13.3, the Fundamental Theorem of Line Integrals, Video 1. Full disclosure, this is take 3. The first take, I made a mistake early on, and at the end it was a train wreck. The second take, I got all the way to the end and realized I made another mistake. So I decided to actually summarize the first 2 videos I was planning on doing for this series, which was to take us down an intuitive path, and then the second video was to summarize it, but we'll just do it all in one video. So what have we talked about so far in chapter 13? We've talked about vector fields, which is a function that says, give me an ordered pair or an ordered triple, and I will turn it into a vector. And then we talked about line integrals, which was the extension of a single variable integral, but instead of being over an interval on the x-axis or on the y-axis, it's defined on a curve anywhere in the plane, in the xy plane. Actually, it can be in any plane or anywhere in space. One of the big results in Calculus 1 is the Fundamental Theorem of Calculus. And without writing it all, you can look on page 295 of your book for the Fundamental Theorem of Calculus, commonly abbreviated FTOC. Although it actually has 2 parts. One part of it basically says if you have a continuous function f, then the integral from a to b of the derivative of f of x dx. Well, you know how this goes. To evaluate an integral, you first calculate the antiderivative of the integrand. In other words, you take the antiderivative of the derivative and then evaluate it at the limits of integration and subtract the results. Well, the antiderivative of a derivative is the original function. So we would just evaluate it at the upper limit, evaluate it at the lower limit, and get that the value of this definite integral is just f of b minus f of a. Well, that made calculus kind of easy, unless you really wanted to do a bunch of Riemann sums and limits as n approaches infinity. No, you don't. So it stands to reason that if there's a fundamental theorem of calculus way back when we first learned about antiderivatives and definite and indefinite integrals, then is there a fundamental theorem at this point when we're talking about line integrals? And the answer is of course, because otherwise we wouldn't be talking about it. So how to make the transition? Well, when you're doing the fundamental theorem of calculus, you have to start with an interval from a to b, usually along the x-axis if it's dx, but the variable is irrelevant. It could be on the y-axis. When we made the transition to line integrals, we lost the restriction of saying we must go along the x-axis or we must go along the y-axis, and we started looking at any path or any curve in the xy plane. It can be in the yz plane or the xz plane, but we focused mainly on the xy plane with the understanding that it was defined analogously elsewhere. We also could define a line integral in space with a curve going through space, but let's not dwell on that right now. So if we're going to make the transition from original fundamental theorem of calculus to fundamental theorem for line integrals, then we need to first transition to a curve as opposed to just an interval. Now, so we're going to make the curve a smooth curve, and honestly it can be a piecewise smooth curve, meaning that your path can have a finite number of sharp corners, but as long as the rest of it, as long as it's smooth everywhere else, we're okay. But if we let C be a piecewise smooth curve given by the vector function r on an interval of t values from a to b, and if f is a differentiable function of 2 or 3 variables, so it's a function that says give me 2 or 3 numbers and I'll give you a number back, and whose gradient vector is continuous on C. Remember, the gradient vector is just an example of a vector field because this function says give me an input and I'll give you back a vector. Then how does the fundamental theorem of line integrals go? Well, the setup would be a line integral. But for the integrand, instead of the derivative of a function, we'll take the gradient of the function. And of course, dot dr, one of our setups for a vector function. A line integral. Well, our standard approach to evaluating a line integral was to transform it completely in terms of the parameter t, and then attack it like a regular integral. So if we're going to do that, this is going to get integrated from a to b. Our delta f can be represented as delta f of r of t. Remember, r of t basically says, give me a t value, and I'll give you an x, a y, and a z, if there's 3 variables. And then f says, give me my partial derivatives and insert your inputs, and I'll create a vector function for you. Dot, well, dr is just r prime of t dt. We've hashed that out before. So how do you evaluate a dot product? Well, a dot product is just the sum of the products of the corresponding component functions. So we would have to take the I component function on these and multiply them, the J component functions and multiply them, the K component functions and multiply them, and then take the sum. So let's think about what the component functions are. This is the derivative of f, partial derivative of f with respect to x. This would be the the derivative of x with respect to t. And the same thing for the remaining component functions. Partial derivative of f with respect to y times the derivative of y with respect to t. And when I say the derivative of y, I mean the y component function in this vector function. Same thing for the z's. Partial of f with respect to z dot dz dt. And we still have the dt on the outside. But wait a second. This might look familiar. If you look on page 649, this is part of a chain rule for multivariable functions. And without writing that chain rule on the board, I'll just tell you what it says. It says that this is how you calculate the derivative with respect to t of f of r of t. And then we still have this dt. Well, this is just a scalar function now. Yes, r of t is a vector function, but its component functions go into this multivariable function and return a single value. So this is a scalar function, but more specifically, it's the derivative of a scalar function. Well, the Fundamental Theorem of Calculus says the derivative of a scalar function as the integrand, when it gets integrated, you just get back the original function. So in other words, the integral of the derivative is the original function, and we just evaluate it at the limits of integration. So f of r of b minus f of r of a. And suddenly we got something that looks like the original Fundamental Theorem of Calculus. The line integral of a gradient is equal to the original function evaluated at the end point, the terminal point of the curve, minus the original function evaluated at the initial point of the curve. Remember, a is the value that you put into r to get the initial point. The initial point isn't a, the initial point is r of a. And b is the value that you substitute into your r of t to get the terminal point of your curve. So this is just function evaluated at the end of the curve minus the function evaluated at the beginning of the curve. So it gives us a really handy way to calculate a line integral if we know that the integrand is the gradient of something. In other words, if we know that the integrand is a conservative function. Remember, a function is conservative if it is the gradient of another function. And that original function is called its potential. Well, that's pretty convenient. But it kind of raises some questions about how we can tell whether or not a function is conservative, if a function is the gradient of something, just by looking at it. We'll explore how to determine that in videos to come.